Alright, hi everybody. I'm going to talk to you a little bit today about how to use the Broyden function to solve the 2D Rosenbrock, or to solve a 2D Rosenbrock function. So a 2D Rosenbrock function is an optimization path that sometimes known as the banana function or a valley function. So if you can see here on the right, that's kind of the general view of what the Rosenbrock function is. And as you can see over here on the left, the actual function of the Rosenbrock. So we're going to go in and we're going to code it and use the Broyden method along with the Sherman-Morrison method to try to run a calculation and try to minimize these. Okay, so first let's bring in all of our libraries. So let's bring in JAX, the super powerful tool. If you wanted to see me talk about some of the other stuff that JAX does, I have a couple other videos. If you want to hear me explain more about the Broyden method with the Sherman-Morrison equation and just some other fun facts, especially when it comes to this coding. You can take a look at some of my other videos, or the previous video from this set. So let's bring in all of our libraries. So we're bringing in JAX, NumPy, and then some config. The config will help us keep things really easy and small, so we're not trying to run a whole bunch of extra code that we don't need. JAX enable 64. Get this to be true. Now we need, so from our scientific Python, the optimize library, we're going to take a bunch of important ones, so root, minimize, and nonlinear constraint. Okay, so these are all the libraries we're going to need. Doesn't seem like there's a problem yet. Oh, nope. Okay, there's a problem. What did I do wrong? JAX enable config.update quote JAX _. Missing something important. Need an X there. Whoopsie daisy. A nickel for every time I type something wrong when trying to create function, or when trying to code. Probably have about $1 million by now. Okay, we're just going to define a variable in our function callouts, so we can use it. This will just be our absolute minimum, as it is just close to 0. We don't really need anything running too wild on us. So let's define a function. So what do we want? So we want to return an array of numbers. So get the JAX NumPy array. Then, well, to help define our function, let's go with the JNP dot sign of x0 plus 0.5 times x previous minus x1 inside the parenthesis, and we want to cube it, and the whole thing minus 1. So we're defining two functions here, 0.5 times x1 minus x is to be cubed. And we're going to add the whole thing plus x1. And that should be to 1. Let's see. Okay, now we have a function defined. Ooh, sweet new errors. Okay, so to help define our Broyden update methods, let's call this what it is, the Broyden update method. And since we're not putting in the Sherman-Morrison yet, we will later, but for right now, we don't need it. So our x is going to be 0. We're going to set some zeros. And now our j, if you remember from our previous video and anything we've done, that's going to be our Jacobian. And it's nice because Jax actually has a function Jacobian, and we have to define what our critical variables are. So we'll be using func in x, and then f equals the function of x, just for short things. Now we're going to run a little bit of for loop. So this we're going to set an iterable loop. We're going to set up an iterable loop to help solve our Broyden method from the first set of Broyden method from the previous video. So we need the Jacobian and the negative function value. And the whole thing is plus x. And now we need the derivative of x, or the delta x, not derivative of x. So that's going to be our our next up value, xp. So then our fp is a function of xp. F equals our function, or iterable function value, and we need to iterate the xp again. And well, what do we want to see? We want to see our x and function of p, or function value. Now it's time to set up our stop point, unless you want to see about 80 lines of spit out. That all talks about how close we need to get to 0. Well, we don't need super high accuracy, so we'll put this as 1 to the negative 12th. Missing something there. Gotta break the code. Excuse me. Okay. Oh no. I messed up my indent. Need 1. And I need to put this in line. So, okay. Now here's the actual, Broyden method here. So we're using j plus j and p outer as a function of fp and dx divided by j and p of ln dot dx squared. Okay. See what we get. Alright, pretty sweet. We got some real answers. See, as our function, we have a lot of iteratable values, and we end up going really far into this function, and we're missing something. So with the Sherman-Morrison method, we're going to see it actually go into practice and see if it does make things more accurate and kind of how it affects the Broyden method. Okay, so to change this, we're going to add some new stuff, but kind of following along the same lines of defining a function. So we're going to define Broyden. It will contain a function x j equals none. Our max iterations equals 100, and our verbose equals 0. End it. Now we need j equals jax. So we're just going to set it up again. Pretty similar to how we set it up above with this Jacobian function x value. And if just, setting up some, there's definitions of functions, so if we run this function and we don't have any Jacobian values, then we shouldn't be running the function anymore, otherwise we would go to 100 every time, or pretty close, or we'll have just a lot of extra iterations that don't really need to happen, which, thank goodness, we can set this up so we don't have to wait for our computer to run infinite numbers of calculation, or 100 calculations, while we wait for our function value to return something it got in the 5th iteration. Okay, so that's our definition. So those are our definitions for the new Broyden function. Now let's put in some more information. So we're going to go with 4. So now we need to set up our iterable calculation. So range for the max iterations. Set it up just like before. XP equals. Actually, we're going to change it just a little bit. So we're going to set it up so that x equals the Jacobian inverse at function f dx equals then we want to continue to run these functions. FP. So, good thing to think always, at least while I set up these, is a lot of, or when you're typing these commands, sometimes you'll pop up with a menu. There's a very wise man that once said, when you see these menus, you shouldn't get scared or intimidated about what's going on. You should be excited, as there is much more to learn as you press through your code. So we can bring out all of our values. Don't have any capital F's. Just gotta set up our equations. Is less than or equal to 1 e to the negative 12th. Then we want to break it just like before. We don't want our iterations going to too exact. Excuse me, because it takes more time and isn't going to give us much more information. Okay, so let's break down a couple times. Now let's define some more variables. So our u equals jmp dot expand. We need to expand our dimensions. Expand dims. pretty cool. Luckily there's a lot more into the library of expand dims than just what we're going to be using it for today. And a lot more applications that I personally don't quite understand very well. So this UV function is part of our Sherman-Morrison method. It is something we talked about in the last video, but these are two primarily vector arrays, and we'll be using a transform to get them to what we want. So now we want our inverse Jacobian, which equals the inverse Jacobian minus the inverse Jacobian at u at v dot t at j inverse divided by 1 plus v dot t at the Jacobian inverse at u. So for those of you who haven't seen, this is the Sherman-Morrison function. And I'll make sure we define everything. Okay, let's run it and see what we get. Typing. I am oh so great at it. There we go. That's if you didn't notice, it looks pretty similar to our last line of the Broyden method to begin with. So this this method or this part right here, this is the last iteration. This is the most accurate iteration. This is the answer to our problem. And now that we've set it up, our Broyden method has now done the same thing, but in a lot shorter, by using the Sherman-Morrison method. And well, the function we've defined is our 2D Rosenbrock test function. We've used the Broyden method to define and solve, as well as the Sherman-Morrison method to kind of cut down on some of those iterations, and looks pretty sleek doing it. So this will be the end of this video. Check out my next ones. We'll talk a little bit more about Lagrange multipliers and some slack variables, and we'll end up using it to solve our 2D Rosenbrock functions with some pretty specific constraints. So now that I've gone through all this, we'll make it a little bit harder just to see what our code can do. All right, thanks. I'll see you next time.